Hi everyone, welcome to my YouTube channel, and in this video we will look at problem 1383 from Leetcode. So here is the problem statement, and pause this video for a second. This problem is a little bit difficult. You may already have seen how to solve this problem by just looking at the title of this video. But yes, so this one we will be using greedy approach, but I really want you guys to try to come up with like pseudocode for this problem. So let's look at my solution together then. Let's first talk about the observation. What do we have to find? So this is the example, like this is the equation that we do have to, find. So S is some, so think of S as some set, and we basically have to maximize this quantity, right? Over all like possible combination of set that we are given. So we have two arrays, right? We have speed and efficiency, and then we have n engineers, right? So we can have what if we are given, say, if we can pick k engineers out of n engineers, then we can have n choose k, right? So we have at least like lower bound of n choose k combinations. And because we can also choose up to k engineers, meaning that if we are given n engineers, we can, and our k is say 9, let's say n is 10, we have n like 10 engineers total, and we can form a group up to 5 engineers. Then we can have how many ways, like how many combinations can we think of? Well, we have 10 choose 1, 10 choose 2, 10 choose 3, 10 choose 4, 10 choose 5. So that's a lot of numbers. So this maximize will be, we have to maximize over all the possible combinations, right? 10 choose 1 all the way to 10 choose 5. And then we also have this minimum here, right? Say if we have 5 engineers, like among 10 engineers, then efficiency will be the minimum of those 5 engineers we chose. This problem is, like, if you think about it, like this problem is a little bit difficult. Like, how should we do this problem? Like, do we have to enumerate all the possible cases? Well, in that case, the time complexity will be enormous. So we definitely do not want that. So how should we do this? Like in this case, when we have to, consider two variables here, like in this case, we have to maximize and then we have to minimize. I would say the first thing is maybe we can fix one quantity, like quantifier. In this case, maybe we can, fix like this maximum, or maybe we can fix the minimum, right? So I would say in this case, since we are dealing with the minimum, like here, maybe we can fix the efficiency. What do I mean by that? So that's the key part. I think that's the hardest part, like to see the problem. So for instance, let's use this example, and we have 6 engineers, right? N is equal to 6, and we can choose up to 3 engineers. So that's k. Let's say we pick engineers with speed 1, 5, and 8. So there will be this guy, these 3. And then in that case, the minimum of those 3 numbers here, efficiency will be 2. And then the speed total, like the speed will be 1 plus 5 plus 8. So there will be 14 times 2, 28. If we pick, say, the first 3 engineers, then the minimum efficiency will be 3. And then the speed will be 15. So we have 15 times 3, that will be 45. So notice that if we somehow, well, we first have to, I would say, combine these two arrays. So there will be, we can have an array with, say, first coordinate will be speed, second coordinate will be efficiency. So we can maybe, form an array, and then we can try to say, sort this new array with efficiency first, and then from the decreasing order. What do I mean by that? Let's just create a new array. Like, so here I gave a name for this new array, and then we combine these two arrays. So we would be, and then we sort this based on efficiency in decreasing order. So that means the first guy will be this guy. What is it? 9 and 1. So engineers with speed 1 and efficiency 9, that guy will become the first element in our new array. And then the next one will be 5 and 7. Third engineer will be 2 and 5. So why are we doing this? Well, so let's see. So that's a very good question. K is equal to 3, right? So when we run iteration on this new array from like the from the first guy to the last engineers, then initially we have one engineer. Well, we can calculate the performance here, right? The performance will be 1 times 9, so there will be 9. And then the next one, well, we can either calculate this what is it, performance of this second engineer alone, or we can just calculate the performance of these first two engineers, right? And then we just take the maximum of the previous value and this new value, and so on. So let's say when we are on the third engineer, then we can calculate the performance of the group so far, right? So there will be these three guys, engineers. The maximum, so the efficiency will be 5 right here. We don't have to take the minimum here because we are on the decreasing order, and as we iterate along, this will be the minimum here, right? And then we just have to sum those three numbers and then find the performance here. Okay, how about when we are on, say, this guy, the fourth engineer? So as we iterate along this new array, we can store speed of these engineers into some data structure. And then when we have, say, more than 3 elements in this new data structure, let's just call it stack. Then, like, as we iterate along here, we do not want to keep calculating the top 3 speeds again and again. Like, how should we calculate this efficiently? So I would say we can introduce heap as our data structure for this, and so there will be this guy. So let's try to run a simple simulation here. Say we are starting with here, and then our stack will be, since it is initially empty, we can use heap push with this 1. So our stack will have 1 and our efficiency will be 9. And then our performance of this number is just so far is 9. And also remember, stack in this case is the min heap, meaning that the smallest number is on the top. What do I mean by that? When you invoke a function called heap pop, heap q.heap pop, and then we are doing that on this stack, then we will get rid of the smallest number in our stack. Now we are on the second engineer. Forget about this. So we are on the second engineer, and we push this 5 into our stack. So this is what our stack looks like. Our efficiency will be 7. We can calculate the max performance here, but let's forget about that for now. Now we have a stack with length equal to 3. Okay. But then, so far our max performance here will be what? It will be 40, because we have sum of this speed will be 8, and then our efficiency is 5. Now when we have k is bigger than 3, then we do not want to, when we have more than 3 elements here, then remember we have, so our k here is equal to 3, and we cannot have more than 3, right? But then in Python we have a heap push pop function. What does that do? So in this case, if you use heap push pop with stack and 1 here, here, so we are looking at the fourth engineer, and then the speed is 10, so it will be stack comma 10. So when you use this function, remember we had 152, and then here it will be what? So 10 will go inside because 10 is what? It is bigger than the 1. So 1 will be popped, and then 10 will go in. So this is our new stack, and then we can calculate the max performance of this stack. And then we know that efficiency is 4, and then the sum of this speed is 17, so we get 68. So that's something that we can do. So here, and then when we are on the fifth engineer, we can keep doing this. So are we done yet? Well, we are not quite done yet. Why is that? So if you look at here, I kind of mentioned this before, but Like here, I have not calculated the max performance here, even though I can technically calculate the max performance here. Remember, k is equal to 3. That means we can choose engineer, 1 engineer, 2 engineer, or 3 engineers. We do not have to just, it is not just our group has to be k engineers. So it can be up to k engineers. So we can just add, so we do have to calculate the max performance even if the length of stack is less than k. But that's very easy to do. So let's look at the code here. So this is our code. Our stack is the heap structure, min heap. So this is our min heap, and we have an answer variable initialized to be 0, and we also have a modulo here. Then we have new array. That's the one you just saw here. That's the new array here. Then we'll be using the zip function, and so that's how we create our new array. And then we sort this array using in a descending order, and then we will be sorting this based on efficiency. So that's why we use lambda function here. And x of 1 means this we are sorting this based on efficiency. If this is equal to 0, then we will be sorting this based on speed. And then we set total speed equal to 0, and we will be iterating this for loop here. If the length of stack is less than or equal to k minus 1, then we keep push, we will be building our stack. And then as we build our stack, we still have to calculate the answer here. Remember, think about, say, this example. So if we have speed of 1, 10, and 1, efficiency is 3, 9, and 3 with k equals 2. The maximum performance here is 9 times 10, 90. Right here, we just pick the second engineer. They will give us the maximum performance. Even though k is equal to 2, that does not mean we have to choose a group of 2 engineers. We can just choose second engineer, and that will give us the maximum performance. So that's what's going on here. We still have to calculate our max performance here, and then we just take the maximum here. So that's for the case when the length of stack is less than or equal to k minus 1. And then when length of stack is equal to k, then we have to use this heap push pop function, and then we modify our speed, and that's gonna be very easy. So whatever number we popped, we stored it as a pop variable, and then the number we just inserted, the number we just pushed, there will be new array I, 0, and so we can keep updating our total speed in this manner, and then we can calculate the answer by taking the maximum of each previous answer and with this new performance number. And then when we exit the for loop, we just take the modulo here. So I think this part is a little bit tricky, like heap push pop, but if this doesn't make sense, you can try to say come up with a toy example and then see how this code works. And so let's see the code. Okay, so here is the code, and let's run this together, see what we get. So that's for this problem, and so this problem was a little bit difficult. I couldn't solve this in 1 hour, so it took me a while to find the pattern and how to write a concise code. The presentation you just saw, that's at least how I approached this problem when I saw this problem. And yeah, so I hope that helps. If my video helps you guys understanding this greedy approach, then subscribe to my channel, give me thumbs up, and I will see you next time. So don't get discouraged. I think greedy is a little bit harder than dynamic programming. Actually, those two topics are two most difficult topics in algorithm, this coding problem. Greedy is a little bit difficult. You do have to show why greedy approach works here, and typically to show why greedy approach works, you have to use induction to see why this works. So typically the way you prove greedy approach is you do that by contradiction. So you start with contradiction and you can derive contradiction. So when you do that, you can show why greedy approach works. But in this problem, I didn't show you why greedy approach works. but you can try that on your own. Yeah. So anyway, that's for that. I will see you guys next time. Bye bye.